Why AI? Well, ever since computers could hold images and process them, we also wanted them to understand what's in the image, to know that this image contains a cat, and this is a person, a cup of coffee, and here we have an airplane. Simple task, really, but it wasn't that easy 10 or 12 years ago. Today, with deep neural networks, we can not only detect that this is a face, we can also know the emotion of this face, or to detect a specific person within a crowd. Amazing, really. Today, I'm going to tell you about this journey from the place we've been in 12 years ago to where we are today. I'm going to talk about this journey not only because I find it fascinating, really, but also because I think we can learn a lot of it for the journey we still got ahead. Hello, I'm Ori Ben Yitzhak. I've been exploring algorithms for more than 20 years in the industry, and the last 10 years of them are in the area of computer vision. Today, I'm working at Medtronic AI Group. The three beautiful guys you've seen before are my own three kids. And I'm going to tell you about this journey because I've been there, and I think it was just great. So let's start with a relatively simple task for computer vision. It's the reading of text for natural images. By the time we had this problem on our table, the problem of OCR was already solved. Reading printed text was solved by holding a bank of all characters in many fonts and just finding the best fitting one in the bank. But you cannot hold a bank of all characters in natural images, right? It's infinity. So what do? We started by writing heuristics. Well, if it's a vertical line, probably an I, right? Or a 1. So let's look at the top. If the top is leaning leftward, it's a 1. And if the bottom and the top are identical, it's probably an I. And what about lowercase l? And oh, the line doesn't have to be vertical. It could lean to one side or another. And L and 1 are not that easy to detect. So soon enough, we had a bunch of rules and exception to the rules, and we aggregated rules, and we created hierarchy of rules. There was a jungle of rules. And the problem was, well, fairly solved, but not great performance. And we couldn't do anything better because it was just too complex. No person can hold this entire complexity in her head. Luckily, at about this time, the early days of machine learning started to emerge. Tools like SVM, random forest, random fern became better and better, and they became quite good classifiers. One thing we should remember, though, they were not image classifiers, right? What did they classify? They classified vectors. When receiving a bunch of vectors with labels, they learned something, a kind of separator or a decision tree, internal structures that help them at runtime when receiving new vector, find the best label for it. Okay, so we got great vector classifiers, but we want to classify images, right? So what do? We try to squeeze an image into a vector. We usually cut the image into small sections, and we look for numerical features in those sections, like how many gradients do we have in each direction, or how many pixels we have in each color. Or we can compare this snippet of image to a filter and see how good is the similarity between them. Or we could compare to many filters and aggregate the similarity to all of them, right? And how good is our classifier going to be? Well, just as good as the features we extracted. If we manage to get the essence of this image in those features, we're going to have a great classifier. But if we didn't, well, tough luck. SVM was already a strong enough tool to solve this problem of natural images text. Why was it strong enough to solve something we couldn't solve by heuristics? Because it found the optimal classification for us. We still had to extract features, but the classification was calculated by the machine, and it was calculated to be optimal to the data we gave it. The next huge leap forward came with neural networks. Now, neural networks has been there for a couple of decades. Most of this time, they weren't such a great tool, and they weren't used because they didn't solve problems, real life problems. The great leap forward came when deep neural networks were presented. And for the sake of computer vision, when convolutional neural networks were presented. So let's talk a little bit about what does it mean, deep neural networks, and what the hell is convolutional neural networks, right? So deep neural networks mean we have lots and lots of layers of neurons. And a lot of neurons in the net, and tens of layers and millions of neurons, maybe more. This is very powerful tool, and it solves problems. But what helped computer vision problems are the convolutional neural networks. By the way, they were presented together. They made the big step together. So convolutional neural networks are layers that have are networks that have convolutional layers at the bottom of them. Okay, I didn't say much, right? Convolutional neural networks has convolutional layers, but what is it? So here is what it is. Please bear with me a little bit. The bottom layer, the convolutional layer, has small snippets of the network looking at different areas in the image. There's a snippet for each area in the image. And the small snippets that look at different areas are exactly the same. Not only by architecture, but also they are trained to have exactly the same weights in them. And the same weights means the same neural network. It detects the same features, okay? And what are the features it detects? Here are the features detected by the bottom convolutional layer of ResNet 50. ResNet 50 is a very popular computer vision neural network. And here are the features. What are they? Well, it's a bunch of filters, right? The same filters we used to have with SVM, but now they are not handcrafted filters. Now it's a filter that the machine calculated to best fit the data at hand. And these are just this is just the bottom layer. It contains very simple features, right? Vertical lines, dotting, things like this. But the layers above it are going to be also convolutional, and they're going to extract some more complex features, like an eye of a person, an ear of a cat, a whale's tail. And the entire network is going to have some fully connected layers above all it, and the fully connected layers will have those complex features to decide with them and classify the image. Amazing, really. We have lots of different architectures for computer vision problems and solutions, but trust me, they all have bottom several convolutional layers. So why is that? Because the convolutional layers extract features, and this is what we need. What did we have so far? Remember, we started with heuristics. We manually extracted features from the image and we manually wrote rules to classify them. And it wasn't that good. We gained more power when we switched to early days machine learning, where we still had to extract the features ourselves, but the classification was found by the machine. So we let go of the classification and we gained more power. The next huge step ahead came with deep neural networks, where we let go of both of them. Both the features are automatically extracted and the classification is automated. Letting go gave us much, much more power. So what's next? Well, I believe next we need to let go of the things we still do manually. We still do by trial and error. And what are they? We still handcraft our own architecture. We can either select from a great variety of existing networks, or we can build the network architecture from building blocks, and we try the network we assembled, and if it gives us good performance, well, great, and if not, we switch to another architecture. Well, it's basically trial and error. I believe the machine can calculate for us and find the best architecture for our problem. What about activation function, loss function? It's about the same story. We try, and if it works, great, and if not, we switch. Why not let the machine do it for us? Same for other parameters like learning rate, etc. There are already works that progress in this direction. I believe very soon we will not do it manually. There will be a new machine that will calculate all those things for us. And in the further future, well, as you all know, machine learning and deep neural networks are data addicted. They are so hungry to more and more data and more labeling. We keep doing it for them. We keep collecting data and labeling it, and the quality of the network is really very heavily depending on the quality of the data we collected. So maybe, just maybe, in the further future, we will not collect the data for the network. Maybe it will look for data itself. Thank you. I'm Ori Ben Yitzhak, and I love to answer questions.